In this video, I want to talk about functions and what is a function. So you've probably seen these definitions. A function is a rule of correspondence such that for each element in the domain, there is one and only one element in the range. And a little bit more simplified, instead of saying rule of correspondence, you could say pairing. It's a way of pairing inputs, which are the elements in the domain, and outputs, which are elements in the range, and you do so in such a way that there's only one output for every input. Now, I just want to mention that if you're talking about a rule of correspondence or pairing, all that means is that the way how you operate on the input to get the output is just different. So the same input wouldn't be acted upon in the same way. So for example, if I had one function that said y equals 5x versus another function that said y equals x plus 7, the same input to this first function, let's say I put in x equals 3, here I would have y is 15, so 3 is paired with 15. Right? And then over here on this other one function, if I put in 3 and x, I'll get 10 for y. So 3 is mapped to 10 or paired with 10. So you get the ordered pair 315 here. You'd get the ordered pair 310 there as a point. Okay, so it's just a different kind of rule of correspondence or way of pairing. But the real important part too is that there's only one output for every input. That's incredibly important. So let's take a look at just a couple examples. And I'm making them hopefully non-mathy. And then we'll look at some of the mathy examples toward the end. So let's say you talk about a person and their height on a particular day. Now I put the qualifier particular day because if you're talking about a children grow, but not in one day. Or you talk about an adult, unless they have an accident or something like that, and the verb is shrink or something. In general, if you take a person and you measure them on a particular day, it doesn't matter who measures them. As long as they measure the person correctly, you're going to get the same height. It's not going to change. It's not like that person is measured today and today that person's 5'7", and then later on that day they're 5'5", and it just doesn't work that way, right? There's only one output for that person, and the person's the input. Or let's take a look at the price of a gallon of TG Lee milk, and again, it's just a specific brand of milk. It doesn't matter which one, at a specific grocery store on a particular day. Now again, all these qualifiers are so that you're not talking about, let's say you have a gallon of milk, in Alabama on the same day might cost different from, I don't know, something in the Midwest like Mount Ohio. What we're looking for is this. Let's say you're talking about a very specific grocery store on a particular day, and you have a specific brand of milk. If I have 5 people in line, right, and they all have that gallon of milk in their hand and they're ready to cash out, right? They're all let's say the milk for this first person is $4.10 for the gallon. That means all of them, regardless of who that person is, each person's going to be charged $4.10 for that gallon of milk at that grocery store. It's not like one person gets charged $4.10 and the other person gets charged, the cashier just looks at them and goes, today I'm going to ring you up at $7.20. And then another person, they go, I'm going to give you $3.15. I'm going to charge you $3.15, and so on and so forth. That's not going to happen. It's going to be the same price regardless of, because it's for that one input, there's only one output, right? That's the idea. It's not variable. Now let's try a few examples. Let's have you think through them. So let's take a look at the price of an item and the sales tax on the item if the sales tax is 7%. So let's take an input. So pause for a moment and think. What do you think? Do you think is this a function or not? So let's take, for example, a $200 item. At 7%, that would be $14. Is there any way that a $200 item, when you're calculating 7%, would ever come out anything different than $14? Nope, it wouldn't, right? This is a function. And so for each different input, when you handle it, operate on it by multiplying by 0.07, you're going to get only one output. Right? Let's take a look at number of years of education and the annual income. Pause and think about whether is that a function or not. So let's take, for example, sort of this let's say a 4-year degree at a university. Well, it depends. Let's say if I have a 4-year degree and I'm in engineering, or let's say I take a 4-year degree or program and I'm looking at, I don't know, maybe art. And it could be, honestly, the art person could make a lot more money or a lot less, but it tends to be that usually if you major in art, you're probably not going to make as much, right? So maybe the person in engineering might make, I don't know, 60,000, and maybe the person in art might make 35,000, right? Or it could be that you're at different universities. Maybe this person taking engineering goes to MIT and another person goes to a smaller college, right? And maybe they aren't willing to move, and so they don't make that much money. Somebody who's maybe goes to a high-power school, well recognized, and is willing to move may make a lot more money, even though it's the same kind of degree in the same amount of time. So there's a lot of reasons. So the idea is this: there's a lot of factors that affect annual income. And one of them might be the number of years of education, but it's just not as important as some of the others. So it's not going to determine completely what somebody's going to make. So it's not a function. Flying from New York to LA on a particular day on a specific airplane or airline, and the price paid for the ticket. So pause. What do you think? Do you think this is a function or not? So the idea is, this is not a function because somebody could, even though they're flying the same distance on the same airplane on the same day, right? One person might have bought their ticket really early and paid a lot less. One person might be flying first class and another might be flying coach on the same plane, and so this person might pay $2,700 for their ticket and somebody else might pay like $800 for their ticket. So even though they're on the same airplane, it doesn't mean that they paid the same price for that ticket. So this is not a function. Okay. How about number 4? Pause. So volume of a container of water and the weight of the water at a particular altitude. And I just put in there particular altitude because weight does change depending on that. So and I want that to be the factor. So let's say I take a volume of a container of water. Let's say I take, I don't know, a quart of water. Will it always weigh the same? Yes, it will. There's no way to get something different unless you measure out a different volume, but then we'd be changing the input. So this is a function. All right, so every time I pour out the same amount of water and weigh it, I'm going to get the same weight. All right, so for one input, there's only one output. And how about a person and accounts at a specific bank? Well, let's say you're a person, you might have a savings account. You might have a checking account. You might have a money market account. There's so many different accounts a person can have. So this would not be a function. Okay. So there are many outputs for the same input. Okay. All right. So let me just mention here, this sometimes gets students, is it possible for a function to be a function basically and have more than one input go to the same output? Yes, it is. So for example, let's say you're in a grocery store and I said to you, find me all items that cost, I don't know, $5.10. And you can probably come up with several items that cost that. Maybe some fancy rice might cost $5.10. And then maybe, I don't know, some bone broth might cost $5.10, and so on and so forth. And there's no restrictions on the size of the item or weight or anything like that, but just there's going to be several items that end up being the same price, right? So you could have rice or bone broth or something else, right? How about this? Students and GPAs at the end of a semester. So could I find, and if I say at a particular college, I'm looking for students that have a 3.20 GPA at the end of a semester. Sure, there's probably a ton, right? And so there are many inputs. So let's say Maylin has that, and then let's say Carlos has that, and say Sally has that, right? So there's several inputs that go to the same output. But here's the key. The reason it's still a function is if I look at this input, is there only one output? Yes, Maylin only had one GPA at the end of the semester, right, at that semester. Carlos only had one GPA. It wasn't like he was up in the air going, well, gosh, I really don't know what I have as my GPA. No, it's the one GPA. So for each input, there's only one output. Just like for this particular rice, there was only one output. The price was $5.10 that day. And think about a vending machine. Okay, if you look at a vending machine, a lot of times they're set up something like this where you have a letter, right, for each row, and then a number for each column, something like that. And then in each location, you have something that somebody would want to purchase. So let's say Snickers bars sell really well. And so here you have a Snickers bar at B2. And so you know that when you input B2, you're only going to get one output, that Snickers bar. It's going to drop down. Now, is it possible to have several inputs, right? More than one input that go to the same output? Sure, maybe Snickers bars sell really well at that location. So the vendor's like, hey, I'm going to make several of these available. Right? So now you have B2, B3, and B4 are all inputs that give you the same output of the Snickers bar. But we know what's going to happen, right? We know that when I press B3, I'm going to get a Snickers bar. So for that input, there's only one output. It's just that there's more than one input that go to the same output. Okay. Now, why do we define a function as a way of pairing inputs and outputs so that there's only one output for every input? Why do we do that? It's because of predictability. So let's take a look at even the vending machine example. It would not work. Like, you would probably not continue to purchase from that vending machine if you put in B2 and you can see with your eyeballs, right, that there's the Snickers bar, but something else comes out, like Lifesavers. You're like, wait a second, what happened? Or somehow you press B2 and maybe sometimes you get a Snickers bar and sometimes you get a Lifesavers. You're not happy with that either. You're like, no, I know what I want and I want that to happen. So I want, when I put in that one input, I get one output. It's not all over the board. Like I might get, Doritos, or I might get Snickers, or I might get Lifesavers. That's not good. That doesn't work for me, right? Or if you're looking at, for example, an example that we said here where you have 5 people at the grocery store at the cashier line. Could you imagine if they all had the same item, but they get charged different amounts? They walk out, probably, or protest, that just doesn't work, right? So that input has to have the same output. It has to be predictable. That's what you really want. That's why it's defined this way. Predictability. I got to know what's going to happen. And you count on this all over the place. So, for example, take your car. Sure, how your car operates may change over time or under severe conditions. But in general, let's say over the period of a month, for example, your car, or even longer, your car, you can pretty much count on how your car is going to operate. So if you're used to putting, let's say, 10 gallons of gas in your car, you know more or less how far you can drive. Could you imagine if you put 10 gallons in your car and you went 2 miles one day and 400 the other? You'd be like, I know if it happened to me, I'd be kind of a little anxious when I got in my car because I'd be like, well, I don't know what's going to happen today, right? Am I going to make it to work or wherever it is I need to go? So again, predictability. That's what's behind all of this. Okay. Now, here's some more mathy examples. So what happens in the context of math? So a lot of math books, what you'll see is they'll either give you a table or a graph or something like that and say, is this a function? So what you do, for example, here's an example of a particular company, Major Motors, and for each year, what sales they made. So after they tallied up all their sales in the year 2000, they say, well, we made 612,000. Does that change? No. For that input, that's what they made. It's not like, well, gosh, it was 612, but somehow I looked at the books and now it's 520 or it's 125 or whatever. Thousand doesn't work like that. So for each input, there's only one output. This is a function, right? Here, let's take a look at number 2. Cost of sending printed material by first-class mail in 2016 at the post office. I don't know why there's 2 W's and 2 P's. I have no idea what that is about. Sorry. All right, so what this means then is if I have something that weighs up to an ounce, then I'll pay 47 cents to have it sent. If it weighs 2.5 ounces, I'll pay 89 cents. If it weighs 2.7 ounces, I'll pay 89 cents. If it weighs 2.9 ounces, I'll pay 89 cents. If it weighs 3 ounces, I'll pay 89 cents. In each case, when I go to the post office with a certain package and I know its weight, do I know what I'm going to pay? Yes. There's no uncertainty about what you're going to pay. It's very predictable. So this is a function. But this also is an example of how many inputs have the same output. So in this case, for example, everything that's a little over an ounce, because exactly an ounce you pay 47 cents, but anything over an ounce and up to and including 2 ounces, you pay 68 cents. So if it's 1.1 or 1.2 or 1.3 ounces, all those inputs go to the same output, 68 cents. And let's take a look at the last chart example. Here we have the age of a patient at a hospital survey and their cholesterol. So is this a function? Well, if I look here, I have here somebody who's 53 can have a cholesterol level of 217. Let's take a look here. And this 53-year-old has a cholesterol level of 195. That 53-year-old has a cholesterol level of 241. And this one has a cholesterol level of 193. So just because I know somebody's age, do I know their cholesterol level? No, I don't. So it's not a function. It's not like the post office example where if I know the weight of a package, do I know how much I'm going to get charged? Yes, I do. That's predictable. This is not predictable. Age, so what this is telling me is there's many factors that affect cholesterol. Age is just maybe one of them, but it's not enough to make it predictable. So for this one input, there are several possible outputs. So this is not a function. Okay. All right. And then let's talk about in the graph form, as opposed to the table format. You've probably heard of the vertical line test. You've passed a vertical line horizontally over a graph. If the vertical line crosses or intersects the graph more than once, it is not a function. So if it only intersects once, it's a function. So the idea is, the classic is, so you have an XY axis, a line, and you look at, and it does, just horizontally, you're going this way. What's really happening? Well, what's happening is, let's say I'm checking for this input, right? So on my x-axis here is my input. For this input, where am I mapped or where am I graphed? Here. And notice what I had to do. I had to look, and once I knew my specific input, I would look up or down to see where does it hit the graph. That's why we're letting a vertical line represent a specific input. And then we're saying, well, let's check every input. So we're going to scan horizontally and see, does it cross, as we scan the vertical line horizontally, does it cross only once on the graph? So it only does cross once, so this is a function. So essentially the vertical line represents an input, right? Because you're going to scan up and down to see where it hits the graph. So let's take another one, another example. So let's say I look at a circle, or an ellipse in this case, it looks like. Well, if I just anywhere, kind of almost except for the endpoints, here's an input, and then if I go to look, scan up and down, right? So that's where it becomes like a vertical line. I see that I hit the graph twice, so this is not a function. And let's take a look at something else here. Let's say I had something like this. And as I scan, right, it looks like it's a function everywhere except for here. Right here, I have 2 outputs for this one input. So this is still not a function. And the point I want to make is that it doesn't matter if everything works but one place, one input. So it only takes one input to make a function test fail, right? So one little place out of, I don't care how many billions, that means it's unpredictable at that one spot. So for this to have been predictable, you'd have to have something like this. That would be function. That would be a function. So now, or either this one could be closed and this one open, or this one could be open and this one closed. That doesn't matter, but it's the fact that for this input, you can't land here because it's open. Instead, you're mapped here. So there's only one output, and so it's predictable. All right? Thank you so much for listening.